about ellipses, and the first one is obviously your parent function, which looks an awful lot like what? The parent function for which? Circle, right? Circle. And when you graph it, guess what? It's a circle. It has a center right here at 0, 0. Has a circle just like this. That means its center is at 0, 0. The vertices are at 1, 0 and negative 1, 0. Co-vertices are on the y-axis at 0, 1 and 0, negative 1. There's this thing called the foci, and we're going to use an equation for it. The equation that you use is c squared equals a squared minus b squared. That feels familiar, right? It's almost what? It's almost the Pythagorean theorem. You're always going to use a greater than b because you always want your answer to be positive. Okay? And so I'll show you how to do that in a second. It's a little hard with the parent function one because essentially, bless you, you've got both ones. Okay? The length of the major axis, in this case it's sort of a tie. The major axis is the same as the minor axis. The length of it is 1, 2. And the length of the minor axis is 1, 2. So the answer for both of them is 2 units. It'll be a little more obvious on the next one, which one's the major and which one's the minor, okay? But for this one, just put 2 and 2. So let's talk about the foci. So you use the equation c squared equals a squared minus b squared. And usually the a is the larger number, but in this case, they're both 1. We get 1 and a 1, so we plug in 1 squared minus 1 squared. We get 0. Okay? Obviously, it's not always going to be like that. So let's do number 2, and it'll make a little more sense. All right? So on number 2, we're going to call this standard form. And when you have your equation in standard form, you're going to, things are going to work out really nicely for you, right? For instance, your center ends up being where?
0, 0.
0, 0. So if you have a point right there, you have a center right in the middle. And then you're going to have a stretch and a stretch, right? So think about it. Which one is your major stretch? Up and down, what we call a vertical stretch. And how many units did you go up and how many units did you go down? 5. So if you go up 1, 2, 3, 4, 5, put a point. Down 1, 2, 3, 4, 5, put a point. Where could the 5 come? Where could the 5 come from that equation? The square root of this denominator. You see it? That's where the 5 came from, which makes your vertices at 0, 5 and 0, negative 5. You go up 5, you go down 5. That gives you your 2 vertices, and then your co-vertices is the square root of this number, right? Square root of 9, you got what? 3. So you went 3 this way, 3 this way, and you have 3, 0, and negative 3, 0. Okay? Then when you graph it, if you turned it sideways, it kind of looks like a pair of lips. See it? See the lips? That's why they're called ellipses. No, I'm making that up. Guys, okay, I totally made that part up, but it'll help you remember it, especially tomorrow when we go the other direction. Okay, So the next thing is the length of the major axis. So the major one, just like the regular vertice, is going to be the longer one. How many units is this one? 10. And the minor, going this way, 6. Okay? The only other thing we need to find is the foci. So we're going to say c squared equals, and then we want to take the larger of these two numbers. So the 5 squared minus the 3 squared. So that's 25 minus 9, which is 16, but it's squared. So we do the opposite, which is square root. That means it's 4. Okay? So whichever number is larger, plug that one in for A, because you always want it to be a positive number. Okay? All right. So what happens when we get down to number 3? Number 2 was nice because our center was at 0, 0. Right? You see that? Number 3, where's our center at?
-1, -2.
-1, -2. Do you see where that's coming from in the equation?
Yeah.
Yes. You guys see that? This is the H and this is the K, and the formula, the standard equation, excuse me, is x minus h squared plus, whoops, so you can't see where I'm writing, y minus k squared. This is going to be over A, this is going to be over B, equals 1. Okay, so you've got all these numbers plugging in, and you can see how those numbers are affecting the center and affecting the stretch. Okay, so if we have a center at -1, -2, then we have to look to the denominators next for the stretch. So how this one's going to stretch 6. Take the square root of this. This one's going to stretch 5. So we're going to start from the center. Now, the last one, we got to start from the origin, right? Right at 0, 0, which makes it nice and easy. But when your center is moved, then you got to count from that center. Does that make sense? You can't count from the origin. You got to count from the center. So we're going to go 6 to the right. 1, 2, 3, 4, 5, 6. And 6 to the left. 1, 2, 3, 4, 5, 6. Which makes our vertices at 5, -2 and -7, -2. Okay, and then the other stretch is 5 units. So up 1, 2, 3, 4, 5, and down 1, 2, 3, 4. Let me try that again. 1, 2, 3, 4, 5. And that gives us our ellipse. And that one almost looks like a circle because those two numbers are pretty close together, right? 5 and 6. So when it's a little more dramatic, it's going to look more like a pair of ellipses, okay? So the major axis, that length is going to be, what, double this? So 12. The minor is going to be double this, which is 10. And then let's find the c squared equals the a squared minus the b squared. So what is that? 6 minus 6 squared minus 5 squared. 6 squared minus 5 squared. Then we'll take the square root of it. So I got square root of 11. And I calculated it, and I got a decimal, 3.31-ish. Okay. Question number 4 is pretty similar to 3, so we're going to skip it for now, but you can go back and fill in the vertices, the co-vertices, the length of the major and the minor, and figure out that number. Flip it over to the back. All right, on the back, we're getting into non-standard form. This is called the general conic form. And so basically your goal with it is to get it to standard form by using your algebra skills, right? Okay? So you want it to be set equal, you look back over on this side, you want it set equal to 1. You want a plus sign. You want the x squared and the y squared in the numerator, and you would like some perfect squares in the denominator, right? Because then when you take the square root, you can have them nice and pretty and count out an exact amount. If you had to count out a decimal amount, it's not going to kill you, but you could, okay? So numbers 5 and 6 look pretty complicated, but they're actually fairly easy. They're very close to standard form. In fact, on number 5, all you have to do is add 36 to both sides. And then because you want a 1 on the right, you're going to divide all your terms by 36, which makes this side a 1, right? Okay? And on this term, the 36's will cancel, so you'll have a 1 in that denominator as well. Okay? So this one is actually centered at 0, 0. And you stretch this way 6 units. You stretch the other way 1 unit. You guys see how that one's going to go? Okay? Same thing with number 6. Add the 25, divide everything by 25, and that one's fairly easy. The harder ones are 7 and 8, okay? So 7 and 8, let's take these. Notice we've got now quite a bit going on. So we're going to do a partial complete the square with these, and you'll see how to get them into standard form. So for number 7, we're going to group the x terms together. Remember we did this last week? Was it the circle we did it on? We're going to group the 9x squared and the 72x together. We're also going to group the y squared and the 6y together. And I'm already going to move this 144 over to the other side, just because I can. But you could do that in a separate step, right? Okay. What I notice about these two terms with the x in them is they both have a factor of 9. Everybody see the factor of 9? So I'm going to pull out a 9, which leaves me with x squared plus 8x. I'm going to complete that square in just a second. I'm going to, if I could factor out something of the y's, I would, but y squared doesn't have a coefficient, so it's going to be y squared plus 6y. I'm going to complete that square in just a second, equal to negative 144. Now, to complete the square for the x's, I take half of 8, which is 4. 4 squared is 16, right? But I didn't actually just add 16 to this side. I added 9 times 16. Crazy, right? Because I pulled that 9 out, I have to multiply 9 times 16, which just so happens to be 144. So I have to add 144 to this side, because I just added 144 to this side. Okay, now let's complete this square. Half of 6 is 3 squared is 9. So I'm adding 9 here, which is adding 9 here. Okay, so I'm going to rewrite this trinomial as a factored binomial. So it's the x plus 4 quantity squared, and I have a 9 out front. This one was y, what did we square 3? Y plus 3 squared. And then if you combine all this stuff right here, because these are opposites, you just end up with 9. Okay, but we want the right side of the equation to be equal to 1. So we divide everything by 9. Watch what happens. These 9's go to 1, which is how we want it. And these 9's also go to 1. So we have x plus 4 squared plus y plus 3 squared over 9 equals 1. And now it's in standard form. Okay? So if you get an equation